about correlations of von Mangoldt and DKN.
Okay, thanks for the introduction, and thanks to the organizers for inviting me to speak. It's a great pleasure to be here and talk about this work, which has been partly done at MSI during this spring. So I will talk about the correlations of von Mangoldt and higher order divisor functions, and everything is joint work with Maxime Radziwill and Treetop. And let me start just to make sure that everybody knows what we are talking about. I will define the von Mangoldt and divisor functions. So we write lambda n to be log p if n is a power p and 0 otherwise. And we write dkn to be the k-fold divisor function. So it's the number of ways we can write n as a sum of k things. So it's a generalization of dn, which is just the k equal to 2 case. And then I will talk about correlations of these, but let me start with the twin primes. Okay, so if we want to study twin primes, then this is the same thing as looking at the sum of n up to xa, indicate the function of n is a prime, times indicate the function that n plus 2 is a prime. Okay, so if we can show that this is, say, or something, if this is tending to infinity with x, then we can show that there are infinitely many twin primes. And studying the indicator function of the primes is essentially the same as studying the von Mangoldt function. So we can, understanding twin primes also corresponds to understanding this lambda n plus 2. And this is the thing that I call correlation. So we have a function, say lambda n, and I look at it at 2 points, and I want to know if it's correlated, this values at lambda n and lambda n plus 2, if they are related or not, if there is some correlation going on between some consecutive values of the function or some k-step values of the function. So for the von Mangoldt function, there is certainly correlation. The lambda n and lambda n plus 1 certainly know about each other. One of them is always 0. But then the question is, how about lambda n plus 2 is there? What's happening if you look at the sum of this thing? And if we can show a reasonable lower bound for this, in particular tending to infinity, then we can show that there is infinitely many twin primes. So it's interesting to study correlations of the von Mangoldt function. And in general, I want to talk about, instead of having 2 here, having h here, which is similar. And then, because we can't do twin primes, I want to average over different h's. But let's first state what we expect to be true for such a correlation. So it's a hardy little wood conjecture. It says that if we look at this lambda n plus h, then this should be asymptotic to single series depending on h times x plus big O of x half plus 2 of 1. And this, of course, it would imply that there are infinitely many twin primes and the asymptotic formula for them. And here, let me define this single series. So here this g of h is 0 if h is odd, because then there are not many pairs of things that are both primes. I mean, the difference h, there is at most you have 2 or powers of 2. One of them must be a power of 2 if h is odd. And in cases h is even, this is 2 times the product of primes 1 minus 1 over p minus 1 squared. So this is the so-called twin prime constant, but there is something depending on h as well, which is p divides h, p greater than 2, and p minus 1, p minus 2. So this essentially corresponds to the probability that both of these are primes, because there are some obstructions or some things which affect this modulo small prime. So for instance, if h is 3, then in order for both of these to be prime, n must be 1 or 2 mod 3, not 3 mod 3. So there are some things that become into this sigma series. But anyway, we have very good conjecture about this, what happens. We have a clear main term, and then there's a small error term. But the thing is that we, of course, can't solve it, that this is true. Okay, so this is wide open. And that's why the question I want to discuss is what happens if we average over h. So in particular, are we able to show that Hardy-Littlewood conjecture holds for almost all h in a good range of h? And that's the question I'm discussing today. So earlier, we have shown with Maxime and Terry that if we look at the Radziwill function instead of one Mangoldt function, then we can do this for almost all h with h up to capital H, which just can be like log x if you want. So we have shown it for almost all h, but now for the one Mangoldt function, the question becomes much more difficult. But let me state the theorem so we can see what we can do in this case. So it's myself, Radziwill and T, and we saw that if we take x, that's then h, and h at least x to 8 over 3, say, then we can do this for almost all h up to this capital H. So then we have that is lambda n plus h equals this expected main term plus an error term, which is not quite as good as we could write it here as the conjecture was. So we win any power of log. Okay. Then we have this expected asymptotic relation for the correlation of one Mangoldt function for almost all h. For all but big O of h times log x to minus a h smaller than capital H. So we get it for almost all h, but h must be in this range up to capital H, which is x to 8 over 33. And for the Radziwill function, we were earlier able to do this for any capital H tending to infinity with x. So we had much shorter average over h here. But anyway, we can show that the Hardy-Littlewood conjecture holds for almost all h, where h is in a reasonable short range. And let me mention the previous result for this to get comparison. So the previous result is due to Mikawa, and it's 91. And he showed this for h larger than x to 1 over third plus epsilon. And here we note that this exponent h over 8 over 33 is 0.242424, and so on, which is somewhat smaller than 1/4. And so been able to push this result of Mikawa quite a bit further by going below 1/4. So there is a reason for this exponent 1/3 here. It is twice the exponent that you get if you look at primes in almost all short intervals. So it's known that the asymptotics for counting the number of primes in short intervals is known to be true for almost all h with h up to x/1/6. And here this is twice that exponent for reasons of how the proof works. So we have to make up something new in order to get beyond this barrier. But unfortunately, it doesn't help for the problem of primes in almost all short intervals. We don't get a respective improvement there. Okay, so this explains the first part of the results I was promising. So this is what we get for the correlations of the von Mangoldt function. But in my title, I also have the k-fold divisor function. So let me first motivate a bit why we want to look at the divisor function as well. And the motivation, one of the motivations comes also from the twin primes. So if we look at this problem of doing the von Mangoldt function, there is a close relation to doing the divisor functions. And in particular, let me point out that this we take or expand log of 1 minus zeta. Then this is just using the Taylor expansion of log 1 minus y. We can write this as sum of k from 1 to infinity minus 1 to k over k times zeta s minus 1 to k. And then if we compare the coefficients of the Dirichlet series on the both sides, we get that on the left-hand side, we have a log of zeta. So let's write it. And log of zeta is closely related to the primes. The coefficients are 1 at powers of primes and 0 otherwise. Or not quite. So we have the coefficients are 1 over alpha if we have an alpha power of a prime. So this is the Dirichlet series coefficients of the left-hand side. And on the right-hand side, we get the sum of k from 1 to infinity minus 1 to k over k. And then if we raise this to the kth power, the Dirichlet series almost corresponds to the k-fold divisor function. If it was just zeta s to k, it would be the k-fold divisor function. But in this case, it's, let's say, dk star of n, where this is the sum of the ways that you can write n as a product of k things where none of them is equal to 1 because of this minus 1 here. I guess many people are familiar with this sort of thing. It's called Rinnich's identity. But if you are not, then don't care about it. But the point is that using this sort of identities, or you could use Vaughan's identity or Heath-Brown's identity or whatever is your favorite identity for von Mangoldt function, you can, instead of looking at the von Mangoldt function, you can shift into looking at the divisor functions. If you understand the correlations of all k-fold divisor functions, then using this relation, you will understand the correlations of the von Mangoldt function. So this means that morally, we need to understand dkn, dk n plus h for all k. So in order to understand this von Mangoldt function, correlation of von Mangoldt function, it would be enough to understand the correlations of the divisor functions for all k. And in particular method of proof for the theorem 1, the first step is to use heat transfer identity, which is sort of a variant of Grignig's identity, which is more convenient for us. But anyway, to reduce matters into understanding things like this. Okay, so for this, I should say what's known about this. So k equal to 1, it's trivial, it's just summing, I mean this disappears and it's just summing ones. So it's trivial case. And for k equal to 2, it's known for a fixed h, or for any h you can take h to even grow with x, but for k equal to 2, the divisor correlations are studied a lot and there are quite a good result about them. So it's known for our purposes because it's known for fixed h and with some sort of error term. And, but then if you look at higher correlations, we have that for k greater than 3, that our theorem for the von Mangoldt function works. So for divisor correlations, it also works for k equal to 1 or k equal to 2, but they are already known. So this is known for fixed h. And for k at least 3, variant, and the variant is that there is a different main term. But we can get the same range for h and same logarithmic savings also in the case of the k-fold divisor functions for that theorem. And that's essentially what we do in order to deduce this theorem for the von Mangoldt function. But then this divisor function is in many ways easier than the von Mangoldt function because it's multiplicative. So perhaps we can do better for the divisor function than we can do for the von Mangoldt function. Okay, one more thing I should say that also for divisor function, the previous result corresponding to this our method working and variant of it working and getting the exponent 8/33. The previous result was over x over 1/3 for that one, and it was work of Bayer, Browning, Marasista, and Zhao. So they got the same result as the Mikawa, this x to 1/3, but for the lambda n replaced by the d3. And for the higher or the divisor functions, there wasn't results with h below x to half, I think. So anyway, we get, by the variant of this result, we get that we understand the divisor correlations for almost all h up to this x to 8/33. Well, understanding means that we save some powers of logs. It's quite nice. And another motivation to study these correlations of the divisor function is that they are related to moments of zeta function. So for instance, this, if we look at the kth divisor function, then it's related to kth moment of zeta. So if we understood this very, very well, then we could get information about moments of zeta function. So it's interesting to study also these correlations of the divisor function. And I have another theorem which gives us some information about them. Some more information in addition to this, that the variant of the theorem 1 works. So this is theorem 2, again with Maxim and Terry. And for the divisor function, we can go to much smaller h. So again, it's x to be larger than h. But this time we just request that this h is at least log x to ck for some constant depending only on k. So I should say that for the value of ck, something like 10,000 k log k seems to be certainly acceptable. This is still work in progress. And I guess we can reduce this 10,000 to be something smaller, but we can't get rid of this k log k, and there are good reasons for that. Our method just can't work beyond this k log k range because it's based on looking at divisor function in short intervals, and if we have two short intervals, the oscillation of the size of the divisor function starts to be bad. I mean, then one single term will dominate, and then we are in trouble. So that's why we have to have the range to be at least a k log k, and at the moment it's something like 10,000 k log k, but I don't know what it will be eventually. But anyway, let's just think that it's some constant. Okay, so we get the similar result as there, but for the divisor function. Then the sum of dk n, dk n plus a equals to main term times 1 plus e to the power of 1. So I'm not going to discuss the main term in detail. So it's x times some polynomial of degree 2k minus 2, but I'm not discussing it. It doesn't look very nice, but it comes from the matrix, and we don't have to worry about it too much. But anyway, the point is that we get asymptotic formula for this. This is the main term. So I should say it so that nobody thinks it's m times t. So it's main term. Okay. And this holds for all but e to the power of h values h smaller than h. So you can see the difference between the theorem 2 and theorem 1 for the divisor function is that now we have much shorter average. I mean, we can do almost all h in a pretty short range, but what we have to pay for it is that our error terms are bad. I mean, we just have e to the power of 1 instead of log savings, and we only have that the exceptional set is e to the power of h rather than log savings here. So that's the price we have to pay for going into shorter intervals. And unfortunately, that price is so big that we can't travel from here to the von Mangoldt function. So this doesn't imply anything about the primes because these error terms, or this, in particular, this error term is so bad. So we would need to save some logs here in order to get an implication for the von Mangoldt function. But it's still sort of nice to know that we get for the divisor function, we can get the asymptotics for very short intervals, even though the asymptotics don't imply anything for the von Mangoldt function and probably don't imply anything about the moments of z either. But anyway, we can do it. Okay. So now I have stated two theorems, and I will next start talking about how to prove these theorems. And there are similarities in the proofs and there are differences, but I will start with the general setup, which is same for the both theorems and which is using the circle method. Okay, so what we want to do in both cases, we want to study something like an plus h, and in our case, this is either the von Mangoldt function or the divisor function, but for now it doesn't matter what we are studying, but we are studying the correlation of something. And by the circle method, we can write this as the integral from 0 to 1 of some an e alpha n squared e minus alpha h d alpha. So this integral picks up those n1 and pairs n1 n2 where n1 minus n2 is h. I guess we can dispose of this. Okay. So just to write this condition that write this as n1 and this as n2 and want n1 minus n2 to be h. We can use the circle method in this way. And then we need to analyze this integral. But what helps us is that we only want the result for almost all h's. And the first step, as usual in the circle method, is to split this into major arcs and minor arcs. And we do that first. So we split this into 0, 1. So it's a union of major arcs and minor arcs. And I think my m's look similar, but I don't talk about major arcs. So from now on, it will always be little m when I'm talking about something. So if we write this as S alpha, and I just say that we can handle major arcs, so this is the only capital M that will be here. Handle the major arcs, and they give the main term. And this is a standard thing to do related to distribution in arithmetic progressions and stuff like this. So it's a standard way to handle the major arcs, so we don't have to worry about them. But the point is that we have to worry about the minor arcs. Of course, I haven't yet told you what are the major arcs and what are the minor arcs. So the major arcs are things that are close to a rational with a small denominator as usual, and the minor arcs is the rest. And I think for now we don't have to know anything more about them. So we can get rid of the major arcs, and we just have to study the major arcs. So we study this integral over minor arcs. Okay, and because we want the result for almost all h, we can take a mean of this and sum over h. Okay, and then we want to get some non-trivial bounds for this. This thing in particular that it's for almost all h smaller than the main term, which is of size x times log x to 2k minus 2 in the case of the divisor function. Anyway, we want to study this mean here, and then I have to do a bit of tricks with squaring out and changing orders of summations and summing over h, and we are getting some gain from the sum over h. And anyway, doing this, we first end up with something like sum of 1 over h and integral of h I plus 1 over h goes major minor arcs of s alpha squared d alpha squared. So just believe me that this is the case, but you can morally see it if you square this out and you look at, you end up with alpha 1 and alpha 2, and then if you do the h sum first, then it's only bad if alpha 1 minus alpha 2 is small, because otherwise you win from the geometric series here. So that's why I can restrict sort of a s alpha squared with alpha on a short range. But anyway, I don't go into details about this step, but it's quite straightforward, but you have to do it. But yeah, let's just believe that this is true. So this is related to looking at the average of short integrals of this S alpha thing here. And in order to do this, I do sort of a thing that people often do with circle method. I do take a supremum of something, and then I want to apply a Parseval or something like this for the rest. So what I do is I take a supremum of this integral out for part of this, and for the rest I keep the average. So what I do is I take this is most supremum of alpha in the minor axis, this integral, say beta minus alpha smaller than 1 over h of s beta squared d beta. So this is one component here where I have essentially taken the supremum of the I, and then I have found if there is some point on the minor axis, I just take interval of length 1 over h around it. So this is part of the thing. And I have a second power here, so I am allowed to take out any smaller than second power. So let's say I take power delta out there, and then I'm left with the rest of the thing with a smaller power. So this is the same thing as before, except that now I only have 2 minus delta of these guys left. So I have taken the supremum of part delta of this, and I have left with 2 minus delta. So here delta is anything between 0 and 2. Okay. And this looks sort of familiar to circle method things, that you get these averages of exponential sum, and you have supremum somewhere, and you have a mean somewhere. And then what we want to do next is to estimate these two things and get good estimates for them. Okay, so the normal thing would be to take delta equal to 1. And then this second term becomes, if we, here we are only interested in the upper bound, so we can remove this restriction that we are on the minor axis here. It's just getting larger. And then this is, actually, if we take delta equal to 1, this is 1 here, and we are just summing over all intervals of length 1 over h, and this becomes the integral of everything. So this is the, let's say this is S1 and this is S2. So this S2 becomes integral of everything. Okay, and then we know by Parseval that this is the mean square of the coefficients. And then if we want to prove theorem 2, we are in trouble here, because if we have the divisor function here, then the mean square of the divisor function is, or L2 norm of the divisor function is much larger than L1 norm of the divisor function, and we can't afford to do this. So issue for dk n, the sum of nx dk n squared is known to have size like x log x k squared minus 1. There, remember that our main term had size x times log x 2k minus 2, so it's much smaller. So that's sort of a problem that we are losing too much here. But we can, so this is much larger than the main term. I mean, I haven't given you all the details what bounds we need for anything, but the point is that this is a troublesome bound because it's of size larger than the main term, which is of size x log x 2k minus 2. And that's why we can't take delta equal to 1 in that case, because we get into trouble by this Parseval bound. But we can take delta equal to half in that case, and then we have a 3 over 2 moment there, and we can handle it. So So in theorem 2, when we have h to be small, 1, we need to take delta to be half, for example. And then we have to be very careful about this second sum. And actually, that's the main input for the theorem 2, or one of the two main inputs. The other one is doing S1, but S1 we already know how to do it because we have done similar thing for the real Wheeler function previously, and it's not too much different, but for this S2 term we have to be very careful not to lose any logs there, and we have to use duality and a majorand for this divisor function and things like this in order to be able to handle it without losing any logs. So the result we prove for this related to this S2 is we prove the large value result for this sort of exponential sums. So this sort of result implies a result for the 3/3 moment, but I don't go into details about this, but this requires quite a bit of work to do this. But I don't talk more about it, but it will be in the paper, so you can see it there. But anyway, we have to be careful with the divisor function because of this issue that if we look at the second moment, then it will be larger than the first moment, which means that whenever we use Cauchy-Schwarz, we are lost. I mean, we always end up with the second moment of dkn, and then we lose some powers of logs, and then we are in trouble. And the reason we are really in trouble is that our saving in this S1 term is pretty small. So the usual thing in the circle method is to have some pointwise saving here and use something like Parseval here, and then we are fine. But the problem is that when we are looking at small h, our pointwise saving is very, very small, which means that we can't afford to lose any logs here, which makes us sad. Okay, but from now on I will concentrate on this term S1 because irrelevant to the issues with S2, in any case we need to get some saving in S1. And for the one Mangoldt function, this is the main point, to get saving from S1. Also for one Mangoldt function, we lose one log from using the Parseval, but we will build many logs here, so it doesn't matter if we lose one log or not. And also if you look at the divisor function in the larger range, in particular if h is larger than log x to something tending to infinity, then we will win lots of logs here, and we don't have to care about losing some logs. But at this range of h being a fixed power of log x, we have to worry about losing logs there. But anyway, from now on, I will concentrate on this S1. So in any case, we need to understand this S1. So what we need about is that if we look at alpha, the integral of s beta squared d beta, and recall that this s beta is the exponential sum related to our sequence. So the an is either the one Mangoldt function or the divisor function. So we need to study this, and let me finally say what we need about this. It's the bound like big O of 1 over x times sum of an squared. Okay. It's not very. anyway, we have to have some non-trivial saving here. And we need it for all alpha in the minor-ax. And for approaching things like this, there is a lemma of Garage who says that if we look at this integral of the exponential sum over a short interval, it corresponds to looking at the thing in almost all intervals of length h. And we do this at first. So we write alpha as a over q plus theta. So we take some rational approximation of a over q, and we know that we are in the minor-ax, so we know that we can't have q very small and theta very small. And this theta is smaller than 1 over qq. And then we can use this Garage type lemma to reduce this to bounding. So I will write this down first and then say what's saying. So it reduces to looking at almost all intervals. I mean, we have a mean square over x here of length h. Here we have 1 over h, so it turns into intervals of length h. And looking at the mean of the an twisted by this e alpha n, because here we have that this integral is centered around alpha, so that this is essentially, we could write this as s alpha plus t gamma, where gamma size 1 over h. But so this Garage lemma, which is based on Fourier inversion, it just has a few lines to prove that this, and so this, or this left-hand side corresponds to this thing here, based on these exponential sums being constant on intervals of length h. But anyway, we just believe me, then I say that it's enough to understand this thing here. So we have to just do. And if we didn't have this exponential phase here, then this would be understanding or showing that almost all short intervals we had the correct asymptotics for the one Mangoldt function or for the divisor function. But now we have this annoying exponential twist here that we have to somehow be able to handle. And the thing one could do is, or what we will also do, is to write this alpha as a over q, and then we can reduce this to characters mod q, and looking at averages of characters mod q. And if we took q to be pretty large, like h to half, and looked at this, we would actually end up with this previous result of Mikava and Bayer and al, which would give us this x to 1 over 3, but we want to do something better about this alpha, and that's why we would take pretty small q to be able to do something with the theta. Anyway, I will explain to you what we do next. So if we have a sum over short intervals, and then the typical thing is to use Perron's formula to get instead some mean values of Dirichlet polynomials, and that's what we want to do next. We want to transfer this problem of looking at things in almost all short intervals into looking at mean values of Dirichlet polynomials. So this reduces to bounding this, and furthermore to bounding. And And let me write the expression that we end up with. So what happens is we use the Perron's formula, and then we integrate, open the square and integrate over x and get some savings there, but we have to use some stationary phase method to deal with this alpha thing and things like this. But anyway, what we end up after doing this and after splitting into characters mod q, so there's some technical stuff going on here, but eventually we reduce to bounding 1 over q times the integral of t around theta x. The theta is this, alpha is a over q plus theta, and sum of psi mod q 1 over theta h times the integral from t minus theta h to t plus theta h of the corresponding Dirichlet polynomial. So we had this E alpha n here, and it was a over q plus theta. And this a over q goes into this sum over characters mod q. And this theta affects, then we use the integrate over x and everything else. It affects the stationary phase method so that we get these integrals to be from t minus theta h to t plus theta h. And we have the range t is around theta x, which corresponds to the saddle point that we get from having this E alpha n there. But anyway, after some work, we end up bounding something like this. And this is really our main task. Now here we want to show that this guy here is due over x. Oh, it's not quite correct, but we do over the main term perhaps rather than we do over x, I think. Yeah, we do over the main term. And this looks quite messy. And, sorry, main term squared. Oh yeah, here. Okay, so this would be t prime. dt prime, and here we solved have dt. Correct? Okay. Was there another question? No? Okay, good, thanks. Okay, so this looks quite messy, and well, we would like to just use Cauchy-Schwarz to get rid of this inner integral, and we can do it if we want, and we can bound this just by sum of chi mod q and integral of t around theta x, and then mean of this integral here. Okay, we can get, for this one, we just can use Cauchy-Schwarz here and integrate over T1 first, change the order of integration, and we can get a bound like this, which looks very familiar to people who have been working on these things with Dirichlet polynomials and almost all short intervals. But the point is that if we have a largest h, like we have for the one Mangoldt function, we have this at least x to some power, I mean something around x to 1/4, then we can actually take advantage of this average here rather than just using the Cauchy-Schwarz and bounding it trivially. But on the other hand, if we look at the divisor function and we have h like log x to a, then this average here is very short and we can't use it. We can't do anything useful for it. So in that case, we just use Cauchy-Schwarz to get here. And for this thing with the divisor function, we can use a previous work done by myself and Maxime, which bounds things like this. We did Radziwill function in almost all short intervals, and we can adapt the method to work for the divisor function as well because it's multiplicative. But for the one Mangoldt functions, we can't adapt it because one Mangoldt function is not multiplicative. So,
Sorry.
yes.
So you had alpha near A over Q. Does the A not play a role in the character sum here?
It doesn't play a role. No, it doesn't play a role. It gets deleted, yeah. So there is something which is bounded in absolute value here, like a Gauss sum or something like this. It's removed. Okay, thanks. So let's call this star 1, and let's call this star 2. And to prove theorem 2, we bound star 2 by method of Matomäki, Radziwill. Okay, and if you were here in February, we gave a mini course on this method, so it's adaptation of that, and I won't talk more about it now. And I will use the rest of the time to talk about how to bound the star 1 in the case of one Mangoldt function. So we start by using a heat transfer identity, which is a variant of this unique identity I showed you before, and which allows us to reduce into studying divisor functions, essentially. Okay. So for theorem 1, we decompose lambda n into convolutions. Through heat transfer identity. And it allows us to look at certain type of convolutions for this lambda n instead of looking at the original function lambda n. And doing this, and if we look at h between x over 1/3 and 1/4, then the most difficult term is an equals to something like convolution like this, where this m is between h and x to 103, and we call this D3 type term, because this beta could be a twofold divisor function, and then this is a part of the D3. And because D3 we have 3 divisors, at least one of them must be up to x over 1/3. So we take the smallest divisor out, and we have then the convolution of the characteristic function of the interval with something else. And if we had m smaller than h, we have other means of doing it. If we have a good type 2 bound for it, it's easier. And the most difficult thing is this m between h and x over 1/3. And this is really I think the reason that Mikawa stopped at x to 1/3, because then there start to appear these divisor functions, because we might have m between h and x over 1/3. And I should say that our theorem goes below 1/4, but then we have to also deal with the fourfold divisor function, but up to this exponent we have, we can do it as well. But even in that case, it turns out that this guy is the most difficult one. And let's now simplify the expression we have a bit, because I'll make some assumptions. So let's assume we have, say, q equal to 1 and theta equal to 1 over x to epsilon. So we are at the first place, we are taking our q to be up to x to epsilon, and our theta is something smaller than 1 over x to epsilon in that case. But just for simplicity, let's assume that our q is 1 and our theta is 1 over x to epsilon. And let's, for simplicity, assume that our h is x to 2 over 7 plus 2 epsilon, which is something worse than the theorem I was claiming, but it's much simpler to deal with this case. 2 over 7, so to give you some idea, I just will stick into proving this bigger result instead of doing the whole thing. Okay, and then we have to bound this guy up here. Okay, if we take, okay, let's remove this and going to bounding this. So if we take q equal to 1, we can forget about this. We can forget about this. And if we take theta to be x2 minus epsilon, we have here x to 1 minus epsilon. And we have here, okay, so let's write h1 theta h. So we have here h1, and here we have t minus h1, t plus h1, and here we have our convolution 1 star beta, and we can forget about this because we had q equal to 1. Okay, and well, unfortunately, I don't have time to go into much detail about this, but here we can use Cauchy-Schwarz to separate these 1 and beta, and the point is that we will need to save something in both of them or get a good bound for both of them. And for the term with beta, we can just use the mean value theorem, and for the term with 1, so there is some stuff going on, and what we end up is that this is okay if we can do this integration in a short range for this one function here, m of size m, 1 over m2 half plus it squared dt, and if we can get for this the correct bound, that this is go of h1 1 plus epsilon. And if we had the second mode for all t, so what happens, we use Cauchy-Schwarz and we take a supremum over this t's for this first term with the 1s, and we end up needing something like this. And if we had the second moment of zeta for the short interval of length h1, we would be happy, but we don't. But then we can use, the point is that we have smaller m than what we would get from the approximate functional equation for the zeta, so we can write this as an exponential sum, and we get the saving from the Van der Kolput for this thing here. So let me write one more line here. So if we smooth, we get that this left-hand side is at most h over m times the sum of h smaller than m over h of, and sum of m of size m, and 1 plus h over m times it, and we get that this is smaller than h, 1 plus epsilon by exponent pair. Per 1 over 6. 1 over 6. So unfortunately, I'm running out of time, and I didn't have much time to give details about this. But if you are somewhat familiar with these things, perhaps you can see that this will lead to a sum like this, and that you can use Van der Kolput for bounding this, and you will end up with a bound like this if h is at least x to 2 over 7. And in order to go beyond to smaller exponents went over 7, I was claiming something like 8 over 33, I think, which is a bit smaller than we thought. We have to be more careful here, and we can't just take the supremum, but we have to really use the averaging over t and prove some large value estimates, which becomes more difficult. But let me stop here. Thank you.
Were there any questions?
Did your results about divisor functions say anything about higher moments of data?
So I think the result on the very short intervals can't say anything about the higher moments of theta, but the result on the longer intervals might say something in some short moments of theta or something like this, but we haven't figured it out yet, but we will take a look at it.
What's known under Riemann?
So I don't remember very well. Do you remember? Sorry.
X to the epsilon?
Well, at least x to epsilon, but I think something better is known. I'm some log x to something, I think, probably, but I'm not sure what's exactly.
Okay, if there are no other questions from the speaker.